Alright, in today's video we're going to take a look at some more of the volume worksheet problems for grade 9 advanced science. This is the second video. We'll look at a handful of these problems from the worksheet. Today we'll look at some cones, some pyramids, and some multi-step problems. So first of all, question number 11, a straightforward, almost straightforward cone problem. We're given a picture of a cone, we're asked for its volume, but if you look carefully at the cone, you realize there's a small problem. We know the radius of the cone is 16 centimeters, but we're not actually told what the height of the cone is. The height is this dotted line here, the vertical height. Instead, what we're told is the slant height. The slant height is the length of this edge of the cone. So we're going to have to do a two-step problem to find the volume. We'll start by trying to find the height of the cone, and then we'll move on to find the volume once we have that. Now, do you notice that within there, that picture, there is a right-angled triangle. The right triangle where the height is one of the legs of the triangle, the radius is another leg, and the slant height is the hypotenuse of the right triangle. So let's pull that out and we'll sketch it, and then we'll see if we can find the height. So question number 11. If you know what you're doing, pause the video and try it yourself, or if you're just checking, you can skip ahead to see the answer. So we've got this right triangle. Hopefully you included a picture like this in your answer. The radius is the base of this triangle, 16 centimeters. The height is what we're trying to find for our cone, and the slant height is the hypotenuse of the triangle, 34 centimeters. Now, Pythagoras, the Pythagorean theorem, applies to right-angled triangles. You might have studied that in middle school. What Pythagoras actually said was that if you have a right triangle and you construct squares on the three sides like this, I'm just sketching, but imagine actual squares. Okay, what Pythagoras claimed and proved is that the area of the two squares on the legs, when added together, will equal the area on the hypotenuse. So putting that into words, the sum of the areas of the squares on the legs will equal the area of the square on the hypotenuse. Now, a simple way to write that would be to say leg squared, that's the area of the square on one leg of the triangle, plus the other leg squared, that's the area of the square on the second leg of the triangle, has to equal the hypotenuse squared, which is, of course, the area of the square that's on the hypotenuse of the triangle. Now, I'm using these terms, I hope you know them. In a right triangle, the two sides that meet at the right angle are called the legs of the triangle, and the longest side of the triangle opposite the 90 degrees is called the hypotenuse. Now, some people have learned a squared plus b squared equals c squared. I'm not a huge fan of that just because they often will forget when they're first learning Pythagoras where the a, b, and c have to be. The a and the b are the legs of the triangle, which lead to a squared and b squared, and then c has to be the hypotenuse, which will give you c squared over here. I prefer writing it like this. So let's put the letters in. H squared plus 16 squared equals 34 squared. And so solving, we can put h squared by itself by subtracting the 16 squared. So 34 squared minus 16 squared. Of course, you could evaluate that if you want and put other numbers in there, but I'm just going to do it once on the calculator. So 34 squared, take away 16 squared, equals 900 square centimeters, and that's h squared. So therefore, the h, the height of the triangle, the height of our cone, will be the square root of 900, which is going to equal 30. The square root of 900 is 30 centimeters. So there's the height of our cone. Now we can do the second part of the problem, which is actually finding the volume of the cone. Volume is equal to the area of the base, the circle, pi r squared, times the height of the cone, which we now know, divided by 3. Now some people will say 1/3 times pi r squared h, and that's fine, equals pi 3.14 times the radius, which was 16 centimeters squared, times the height, 30 centimeters, divided by 3. Okay, grab a calculator and evaluate that. Pi times 16 squared times 30 divided by 3, and we get this large, ugly number. The volume is 8,038.4 cubic centimeters. Now, if you get everything up to there, you're doing very well. Okay, that's the volume part of the worksheet. But let's consider significant digits. The radius and the slant height were both 2 digits in the original problem, 16 and 34. So we're going to keep only 2 digits in our volume here. When you multiply and divide with measured numbers, you round off according to the smallest number of significant digits in the calculation. So since there were 2 significant digits in each of the measurements, we'll go and round this off to 2 digits. Right now it has 5, right, 8038.4. We're only going to keep 2 digits, which means the 8 and the 0. And since there's a 3 next, we're not going to round up the 0, we're just going to keep it as 80. And then to show the fact that there's only 2 digits, I'm going to convert that into scientific notation. 8.0, there's my 2 significant digits, times 10 to the power of 3 cubic centimeters. Remember, when you're looking at a number in scientific notation, the times 10 to the 3 is not considered significant. Only the number in front, the 8.0, is significant digits here. All right, the next question that I'll take a look at is question number 13. But let me just say something about question 12. Question 12, the picture here is a little bit overly complicated for this question. It again gives us a slant height of 15. For this problem, if you want to think of the 15 as just being the height of the cone, that's good enough. Okay, so we will consider the 15 to be just the height of the cone, not the slant height as it appears to be in the actual picture. Now the question said if the height and diameter of the cone are divided by 3, what's the effect on the volume? So what I would do there is find the volume of the large cone. I'll just say VL. That's the cone as it's shown here, with a diameter of 15 and a height of 15. So you have a formula for volume of a cone. Go find that volume. Then, if you think of the height and diameter divided by 3, you'll have a smaller cone, let's say VS, where the diameter is not 15, it's now 5, and the height is not 15, it's now 5. So if your diameter and your height were both divided by 3, you can calculate the volume of the small cone, we'll say VS. And then to describe the effect on the volume, why don't we divide those two things like this? And then you can tell me that the larger cone, or the original cone, is so many times larger than the smaller cone. Okay, that would be a way to do it. Now, question number 13, a little bit more complicated conceptually, because it's got several, I think more than one step here, 2 or 3 steps. We have a sphere whose volume is given, and it's going to be dropped into some water, which is in this cylinder. Now, we know that the radius of the cylinder is 4 centimeters. We know the height of the cylinder was 18 centimeters. Now, that probably is going to be irrelevant information. We're not going to need that. But the depth of the water is 12 centimeters. So I know that I could calculate, using this information, the volume of the entire cylinder if I want, but I can also calculate the volume of the water in the cylinder if I want, because I know the radius and the height of the water. Now we're taking the sphere and we're dropping it into the water. Here it is in figure 2, and the level of the water rises. Okay, now the question here is poorly worded. We talked about that in class. It was originally a multiple choice question, but I've changed it to a free response open question. So we're going to calculate the height of the water in the cylinder after the sphere was dropped in, and we can see the sphere sinks in the water. When it sinks, we know it displaces its own volume. So in this second picture, the total volume here will be the volume of the original water plus the volume of the sphere. So now I sort of have a plan of attack. I'm trying to find the depth, the height of the water after the sphere was dropped in. Well, what if we start by finding the volume of the water before the sphere was dropped in? Then, if we add the volume of the sphere, we would then know the total volume of the water with the sphere in it. So there's two steps. If I know the total volume, and I know the radius is still 4 centimeters, I should be able to then go find the height. There's the third step. So step 1, I'm going to find the water's volume in the original cylinder. Step 2, the total volume after the sphere was added. And then step 3, I'll find the depth of the water. There's my plan. So let's start by finding the volume of the water in the original cylinder. So the volume of the water will equal, it was a cylinder, so pi r squared, the area of the base, times the height, divided by, it's a cylinder, we don't divide, it's just pi r squared h, equals 3.14 pi times 4 centimeters squared times the height of the water, which was 12 centimeters. So grabbing a calculator, pi times 4 squared times 12, 602.88. I'm going to not worry about significant digits hugely until the end of the question. So for now, I'll just round this off to 603. If you want to call it 602.88, go for it, but I'll just say 603 cubic centimeters. Okay? Actually, I just noticed the sphere, its volume was given with 2 decimal places in it. So you know what? To be consistent, maybe I'll do the same thing. 602.88. It doesn't really matter, okay, at this point. So there's the volume of the water. Now we're going to add the sphere. So the sphere drops in the water, so the volume of the water plus the sphere, the combined volume, will equal 602.88 cubic centimeters plus the sphere's volume, which was 51.31. Now, depending on how you round it off, your answer may come out to be slightly different, okay? But we won't worry about that. So now, let's add these two numbers together. When adding measurements, we know we round off according to the number of decimal places. So I'm going to keep 2 decimal places in this answer. So 602.88 plus 51.31, 654.19 cubic centimeters. And finally, let's see if we can go find the height of the water at this point. If we look at our formula for volume of a cylinder, we realize that the height can be isolated. It can be put by itself if we divide both sides of the equation by pi r squared. Right now we have pi r squared times h. To get the h by itself, we would divide by pi r squared. So if we take volume divided by pi r squared, we're going to have h, the height. So the height of the water after we add the sphere will equal the volume of the water plus the sphere divided by pi r squared, equals the volume we just found, 654.19 cubic centimeters, divided by pi and divided by the radius, which was 4 squared. equals. Now watch how I do this on my calculator. Okay, you have two choices. You can use brackets here. You can say this divided by, and then open brackets and multiply this stuff on the bottom, then close the bracket and say equals. That's one option. The other option is to take this top number and divide it first by pi, then divide it again by 4 squared. That's how I usually like to do it. If you're dividing by a product, like we have here, things multiplied, you can take the top number, divide first by one of the two numbers on the bottom, and then divide again by the second one. That works when the bottom two numbers are being multiplied. Okay? So if we take 654.19, divide by pi, and then divide again by 4 squared, we get 13 centimeters as our height. Now just to show you what I meant a moment ago, the other way to do that would be 654.19 divide by, open a bracket, and now let's type in this product, 3.14 times 4 squared, close your bracket, equals the same answer, 13 centimeters. Okay? Notice if you typed it in like this, 654.19 divided by pi times 4 squared, divided by pi, you're going to get the wrong answer at this point. Okay? Because the calculator is doing order of operations and you didn't. Okay? Alright. Now technically this answer should have only one significant digit. On tests and assignments, if you're within one digit of what it should have, you're fine. So it should have had one digit because of this 4. I'm going to just leave it as 13 centimeters. If you want to put it the exact correct number of digits, you'd say 1 times 10 to the 1 centimeters, which essentially is 10 centimeters. Okay? There we go. The next question that I'll do is this composite figure. Okay, it's a little confusing. If you look carefully at this picture, we're trying to find the volume of this entire figure. Some people look a little quickly and a little carelessly, and they think the two cones here are identical. They're not, if you look carefully. The bottom cone, well, first of all, do we realize that this composite figure is composed of two cones, so a top cone plus the bottom cone, and then it's also got a cylinder. So if I want to find the volume, I just have to find the volume of those three pieces and add them up. Now the bottom cone is straightforward. We know its height, 40 centimeters, and we know its radius, 21 centimeters, so the bottom cone's volume is straightforward. The cylinder is also, I think, straightforward. We know its height is 35 centimeters, and we know its radius is 21 centimeters, so boom, we have its volume also relatively straightforward. It's the top cone which is a little bit problematic. It's not the same as the bottom cone. How do I know? Well, the bottom cone's height was 40. Pause and do you see what the height of the top cone has to be? Pause the video and see if you can do it. Well, the cylinder's height was 35, and this says that the distance from the base of the cylinder to the top of that top cone is 70. So if the cylinder is 35 centimeters, 70 minus 35, which is 35, is going to be the height of the top cone. So the top cone's height is not 40, it's 35. 70 take away 35 is 35. So now I've got the height and radius of all three pieces. I've got a plan. So let's jump to it. So question 14, the volume of the composite figure is going to equal the volume of our one cone plus the volume of the other cone plus the volume of the cylinder. So that'll equal pi r squared, the area of the circular base, times height, divide by 3, plus another pi r squared h divided by 3, plus pi r squared h, the cylinder volume. Now, if you want to be really, really specific, you might put in there H1, H2, H3 just to distinguish them. They all have the same radius, but I'm not going to do that. So equals 3.14 times the radius was 21, and this is the top cone. We just proved that its height was 35 centimeters. Divide by 3, plus pi times 21 squared times 40 centimeters, the bottom cone's height. Divide by 3, plus pi times 21 squared times 35, the height of the cylinder. Okay, so there's the three pieces of this composite figure. So grabbing a calculator, we can find each one if we want. So 3.14 times 21 squared times 35, divide by 3. Oops. Try that again. 3.14 times 21 squared times 35, divide by 3 equals, for now I'll just keep some extra digits here, 16,155.3, then we'll round it off properly at the end, plus pi times 21 squared times 40, divided by 3, 18,463.2, plus pi times 21 squared times 35 equals 48,465.9. And then adding those three numbers together, so that last number plus the second number, 18,463.2, plus the first number, 16,155.3, equals, and we'll round them off to one decimal since we were adding, 83,084.4 cubic centimeters is the total volume. But of course, the dimensions had 2 digits in them, so I'm going to round that off to 2 significant digits. 8.3 times 10 to the power 4 cubic centimeters is the total volume. So now, if you end up, because of a few rounding issues, maybe you did the problem slightly different than I did, maybe you get something like 8.4 times 10 to the 4, or 8.2, that's fine, okay? Your answer, maybe you rounded off slightly different, maybe you left it like 83,084.4. Well, if that were on a test, you might lose half a point. So if that were a 4-mark question, you might get 3.5 out of 4, okay? All right, I think that's where I'm going to pause. There's a few other questions on here. Well, you know what, maybe I'll do one more. There's a sphere, which we haven't seen yet. We're told the radius of a sphere is 6.7 centimeters. What's the volume of the sphere? So let's try that one. This is question number 16. So the volume for a sphere, our formula was 4/3 pi r cubed. So this should be straightforward. 4/3 times pi times the radius, which was 6.7 centimeters, cubed, equals, grab your calculator, 4/3. Now I'm going to type 4 times pi times 6.7 cubed, and then I'm going to divide by 3. You could also say 4 divided by 3 and then times this, if you like. You could convert 4/3 to a decimal. It's 1.33333, and then multiply if you like. But I'm going to go 4 times pi times this, and then divide by 3. So 4 times pi times 6.7. Now every calculator is going to do this slightly different. You could do 6.7 times 6.7 times 6.7. That would be cubing it. But on this calculator, there's a little button x to the power of, so that's what I'm going to use, to the power of 3 and then divide by 3. So 4 times pi times r cubed divided by 3. 1259.19 cubic centimeters. And of course we should only keep 2 significant digits because of the radius, 6.7. So the volume will equal 1.3 times 10 to the 3 cubic centimeters. Now, if you have 1.2 times 10 to the 3, that's fine, okay? I just rounded off slightly differently than I did. Alright, so there's some more examples of volume problems. If I have not answered a question in these 2 videos that you were struggling with on this assignment, then you could message me on Edmodo and I'll post a video of that particular problem, or you can ask me before class or even in class perhaps. Alright, hope that helps. Use this to study for your test and for your exam as well.